the lecture for March 27th, 2020 for Math 203, Section 001, the chain rule and implicit differentiation. So you'll be seeing these two topics on the midterm exam that is coming up next Friday, that is April 3rd. And you'll also be receiving some more problems on my math lab. Okay, so first we're going to discuss the chain rule. You've already seen actually a special case of the chain rule in the form of the generalized power rule. And then we will discuss implicit differentiation. That is a new topic, but it makes use of the chain rule and also the product and quotient rules that we discussed in Wednesday's lecture. So the chain rule says if you have a composite function consisting of an outside function f evaluated at an inside function g, then its derivative is the derivative of the outside function evaluated at the inside function times the derivative of the inside function. F is the outside function, g is the inside function, and this is a summary of what I just said. What's important is that you differentiate the outside function, you evaluate it at the inside function, but you leave the inside function alone. And then you multiply that by the derivative of the inside function. The generalized power rule revisited. So let's say our outside function is the power function x to the r. Its derivative by the power rule is r times x to the r minus 1. For any function, g of x, and the inside function, h of x is going to be the composite function. Just plug in g of x as the inside function to a power function. So this composite function becomes g of x to a power. And then the chain rule says its derivative will be the derivative of the outside function evaluated at the inside function times the derivative of the inside function. Here notice this is the derivative of the outside function, r times x to the r minus 1. So we get this derivative, it's going to be r times the inside function raised to the r minus 1 power, all times the derivative of the inside function. So you've seen this before. The derivative of g of x to the r power is equal to r times g of x to the r minus 1 times the derivative of the inside function, g of x. As I said, you've already seen this as the generalized power rule. Now, sometimes it's going to be the case that you're not going to know, you might know the outside function, but you might not know the inside function. Nevertheless, you can still use the chain rule to find the derivative of the composite function at a specific value, at a specific input value. So let's say, for example, we have a demand equation for the price of calculators is $86 minus 0.002 times x. Here, x is the number of calculators produced, p is the price per calculator. So it's called the demand equation. The more calculators produced, the cheaper a company can sell those calculators. After 1,000 calculators have been manufactured, let's say the company decides to increase production level by 300 calculators per day. We can ask ourselves, at what rate is the revenue increasing per day after 1,000 calculators have been manufactured? So what this is saying is that after 1,000 calculators have been manufactured, when x is 1,000, the derivative, dx dt, is equal to 300. The number of calculators per day increases by 300. Again, this is only at this production level. Nothing else is known about the number of calculators produced because it's going to vary. The function x is going to vary based on the economy, based on the demand for calculators, based on how well the company is doing and how well sales are going, etc. Now, the revenue obtained from selling x calculators is just x, the number of calculators manufactured, times the price per calculator. X times 86 minus 0.002x, that's the same as 86x minus 0.002x squared. The marginal revenue is its derivative. Its derivative is 86 minus 0.004 times x. We're given this, the derivative of the number of calculators manufactured is 300. That is the rate at which the number of calculators is being produced per day is 300 after 1,000 calculators have been manufactured. Now notice R prime, the marginal revenue, we can compute the marginal revenue at the production level of 1,000 after 1,000 calculators have been manufactured. This is just going to be 86 minus 0.004 times 1,000. The decimal place moves 3 units to the right, so it becomes 4. 86 minus 4 is 82. So that means that after 1,000 calculators have been produced, the rate at which the revenue is increasing per calculator produced is $82. Now by the chain rule, we can compute dr dt. Now dr, notice this is a function, this revenue function here is a function of x only. That is, it's the function of the number of calculators produced, but because x, the number of calculators manufactured, is a function of time, it's an unknown function of time because, like we said before, there were many variables, how the company's doing, the economy, etc. We don't know much about the number of calculators. We don't know much about this function. We do know, however, what we're given is that the derivative of this function is 300 when the function's value is 1,000. So our outside function here is r, and our inside function here is x as a function of time. By the chain rule, we say dr dt is the derivative of the outside function evaluated the inside function. Here, the inside function's value is 1,000 times the derivative of the inside function. We get 82 times 300. Now notice this is only true, right, when we're at the production level of 1,000 calculators. And we get this product, 24,600. This means the revenue is increasing at a rate of $24,600 per day after 1,000 calculators have been produced. So that means the next day, the company is going to, there's going to be, remember, revenue is the amount of money that's in the company's cash register. So this means after 1,000 calculators have been produced, if the company increases the production level by 300 calculators per day, the next day, they'll be getting $24,600 extra in their cash register. That's a lot of money, provided cost of production is not too high. Okay. So now we're going to go over the next topic, which is implicit implication. Well, why do we care about implicit implication? What is it used for? Well, implicit implication is used to find the equation of the tangent line to functions that are defined